Hey guys, 5.10. Welcome back to Michelle's version of calculus. Or welcome actually. Didn't even think about that. Anyways, this is intro to optimization. And optimization is basically finding the maximum and minimum but with like real life situations. And I'm gonna try and make this make sense to you beforehand. Or let's read the problem first and then we'll make it make sense. A rancher has 200 feet of fencing with which to enclose two adjacent rectangular corrals. What dimension should be used so that the let me get a highlighter. Enclosed area will be a maximum. Alright, so basically you want to find the x's or the length and width that gives you the maximum area. Alright, and that's why you're trying to optimize it. And with the process to this, the steps is to first, of course, draw a picture, write an equation that will be optimized, write your equation in terms of a single variable. We'll show that in a second. Determine the desired max or min value with the calculus techniques, which I wrote right here, which is going to be taking the derivative and setting it equal to 0. And that makes sense because we know that maximum and minimum occur at critical points. And that's why you take them and set it equal to 0. And those critical points and all that jazz will kind of help you move on from there. Alright, so cool. We're going to kind of go through this. Intro to optimization, I'm going to show you how to set it up and not actually solve it. Solving it is the next one. So, yeah. So, we know what we have. We know... So, we know that we have 200 feet of fencing. And this 200 feet of fencing... with which to enclose the two adjacent rectangular care is basically perimeter in a sense. It's kind of perimeter-esque, but it also is kind of its own entity. So we're going to go ahead and finish labeling these x's and y's because we're going to have an x here, an x here, and a y here, and a y here. And you're basically all of this combined wiring / fencing is going to be equal or has to be equal to 200. So the formula or equation for this, I apologize, it's going to be 200 equals 4x plus 3y. All right, and that's that's the equation. And the second equation is going to be the area, which is what we're actually trying to optimize, which is going to be area is going to be 2x because that's like the length here. It's going to be 2x times y because that's like the width. Or other way around, doesn't matter. 2x times y is going to be your area. And we're going to go ahead and write this equation in terms of a single variable. And we're going to do it in terms of x. And so yeah. Once again, this is going to be basic algebra. And it's going to end up turning out to 200 thirds minus 4x thirds equals y. And what we're going to do is actually plug in this for the y in the area equation. So I'm going to come down here and just rewrite this out. It's going to turn into a equals 2, I believe it was an x, yeah, 2x times 200, 3 minus 4 thirds, oh, I hate doing that, 4 thirds x, yeah. And that's going to set us up for our area. And once you technically distribute all this, you're going to get A equals 400 3x minus 8 over 3x squared. And that is all intro to optimization is. It's just knowing how to set up your equations. There's always going to be one equation that you're going to want to make in terms of something. It's typically x, but it can be x or y, and you're going to want to plug that in to the main thing that's being optimized. Usually, I think it's called the objective equation, and the other one's called the constraint. So yeah. And in reality, your next step for this, your next steps, you didn't even get to it, would be to find the derivative set equal to 0. And then keep going from there. So yeah, that's kind of it for 5.10.